In this lecture, I provide an introduction to fully homomorphic encryption. So first, I will explain the basic properties, and then I will describe also some applications. So the main application is cloud computing on encrypted data. So that is, if Alice has some private data and she wants to delegate some computation to the server, so she's going to encrypt her data, and the server will process only encrypted information, so that she will not reveal her data to the server. So I will describe the four generations of fully homomorphic encryption. So the first generation with the breakthrough discovery of Gentry with the bootstrapping. But in this first generation, the schemes are relatively slow. Then we have the second generation with more efficient fully homomorphic encryption with schemes based on the learning with error problem and with depth linear construction. So I will explain what this means based on the modulus switching. So then we have the third generation, which is based on computing with matrices. And the advantage is that the noise is growing much more slowly and without modulus switching. And then we have this fourth generation with approximate computation and computing homomorphic computation with floating point approximations. But actually, in this lecture, I will focus mainly on the Dghv scheme from the first generation, because it is quite simple, and for this scheme, the bootstrapping operation is relatively simple to describe. So I will mainly focus on this scheme. So what is homomorphic encryption? So the goal of homomorphic encryption is to perform operation on plain text while manipulating only ciphertext. So and without knowing the private key. And so normally for symmetric key cryptography in particular, this is not possible. For example, if we have some encryption of a message M1 under some key with AES, so some randomly looking ciphertext, and if we have the encryption of M2, then clearly we cannot compute the encryption of M1 XOR M2 without knowing the secret key. So of course, if we know the secret key, we can decrypt the first ciphertext, decrypt the second ciphertext, we compute M1 XOR M2, and we can re-encrypt. But if we don't know the secret key, clearly we cannot do this. But for some crypto systems, with some algebraic structures, such as, for example, RSA, this is possible. So, for example, with RSA, if C1 is the encryption of M1, M1 to E modulo N, and C2 the encryption of M2, M2 to E modulo N, if we multiply the two ciphertexts, C1 and C2, we see that this is equal to M1 times M2 to E modulo N. So this is an encryption of M1 times M2. So this means that simply by multiplying the two ciphertexts, C1 and C2, we can compute a new encryption, the encryption of M1 times M2. So we are computing this product of the plain text while manipulating only ciphertext. So this is of course thanks to the multiplicative property of RSA. So given, as I said, given C1 and C2, we can compute the ciphertext C corresponding to the product M1 times M2 modulo N, and for this we can do it using only the public key, so that is the modulus N, and of course without knowing the private key and without knowing the plain texts M1 and M2. So the multiplication of the plain text M1 times M2 is performed implicitly. So we can write a commutative diagram based on this homomorphism. So for RSA, the homomorphism is the homomorphism of the decryption function. So to decrypt a ciphertext C, we raise C to the power of D modulo N. So the decryption of function is data of x is x to d modulo N, and we see that of course this decryption function is homomorphic with respect to the multiplication. And so we have this commutative diagram. If we start from two ciphertexts modulo N, we can multiply those two ciphertexts. So I write this operation in green because we can do this publicly. So we obtain a ciphertext. And if we decrypt then this ciphertext, we obtain a plain text. but this is we can also follow the other path. If we decrypt separately the two ciphertexts, C1 and C2, the two components, we obtain two plain texts, M1 and M2, and when we multiply those two plain texts, we recover exactly the same plain text. So we obtain exactly the same result for the two possible paths. And also there exist other cryptosystems which are homomorphic for the addition. So for example, the Pi crypto system, if we have C1, which is G2M1 modulo n square, and C2 equals G2M2 modulo n square, when we multiply the two ciphertexts, C1 and C2, we obtain an encryption of M1 plus M2 modulo n. So we are computing by multiplying the two ciphertexts, we are computing the sum of the two plain texts M1 and M2. So we have the same a similar commutative diagram in which we also multiply the two ciphertexts modulo n square, but when we on the plain text side, this corresponds to an addition of the plain text, and of course in both cases we obtain the same result. So we have this Pi crypto system which is homomorphic for the addition, and one simple application for this is e-voting. So assume that every voter encrypts his vote mi, which is simply a bit, into ci equal g to mi and zi to n modulo n square, which is the definition of the Pi crypto system. So we need this zi to n, where zi is a random, to obtain a probabilistic encryption scheme. Otherwise, there will be we will have no security. And now we can aggregate actually all the votes using only the public key, because we can compute the product of the ciphertexts, the product of the CIs, and which will be equal to G to the sum of the MIs times some Z modulo n square. And eventually we can decrypt to recover the message M, so the result of the vote. But the aggregation itself can be performed using only the public key. So thanks to this homomorphic property of the Pi crypto system. So we have basically RSA, which is homomorphic for the multiplication, and we have Pi, which is homomorphic for the addition. But for a long time, the fundamental open problem was to have a scheme which would be homomorphic for two operations, for both addition and multiplication. So this was an open problem until the breakthrough of Gentry in 2009. So I'm going to explain why this is important, why it's really crucial to have homomorphism for two operations and not only for a single operation. So for now, for simplicity, we are going to restrict ourselves to the public encryption of a single bit. So we encrypt either 0 or 1. So for example, the encryption of 0 is a randomly looking ciphertext, and the encryption of 1 is a randomly looking ciphertext. But of course, encryption must be probabilistic. So when we encrypt 0 or 1, we must generate some randomness so that there are exponentially many possible ciphertexts corresponding to the plain text bit. And semantic security means that we cannot distinguish between an encryption of 0 and an encryption of 1 without knowing the private key. And so what does it mean for the fully homomorphic property? It means that if we have an encryption of x, of a bit x, and an encryption of y, then we can compute the sum or the XOR of x and y, and we can also obtain an encryption of the product of the AND of the two bits x and y, and we should be able to do this, of course, without knowing the private key, using only public operation. So on the left, we have the plain text world where we are working with bits. So given the two bits x and y, we can compute the XOR x and XOR y, and given x and y, we can compute the AND, the products x and y. But there is also, so on the right, there is the ciphertext world in which we don't know the value of these bits. We only have ciphertext. So we have the encryption of x and the encryption of y, but we should be able to compute the encryption of the XOR of x and y and the encryption of the AND of x and y. So we should be able to perform the same operations, the XOR and the AND, but without knowing the private key, without knowing the underlying messages. Here on the right, we don't know the value of the bits x and y. We only know that we are computing the XOR of x and y or the AND of x and y. So why is it important to have these two operations? Because this is of course for universality. We know that we can, in that case, we can evaluate any Boolean circuit, because any Boolean circuit can be written with XORs and ANDs. So we can basically homomorphically evaluate any Boolean computable function from n bits to 1 bit. So for simplicity, we can restrict ourselves to 1 bit, but of course by concatenating such function, we can compute any number of output bits. So on the left, we have again the plain text word. So we want to compute the output of this function. So here, for example, a function with 5 bits as input. So we have a Boolean circuit, and at the end we obtain a single bit, the answer, which is f of x1, x2, x3, x5, x4, x5. So that's when we are working with the bits. But on the right, if we have encryptions of these bits, the encryption of x1 and the encryption up to the encryption of x5, we can perform exactly the same computations, but homomorphically. So at the end, what we obtain is an encryption of the result, an encryption of f of x1 to x5. So basically, thanks to these two homomorphic operations for the sum and for the product, we can evaluate homomorphically any Boolean function. And so this enables to outsource the computation, because assume that Alice has some function that she wants to compute on some data, but assume that this function f is quite complex and it will use a lot of resources. She wants to delegate this computation to some server, but she wants to keep this x private. So what does she do? She can encrypt all the bits of xi of x into ciphertext. So every CI is an encryption of each bit xi of x. So using her public key, and she sends these CIs to the server, and the server is going to evaluate f of x, but on the ciphertext homomorphically. So it's going to write the function f of x as a Boolean circuit, and then given the encryption of these input bits, it can, as previously, obtain an encryption of f of x. So we will send back this encryption of f of x to Alice. And Alice can eventually decrypt C into Y, which is equal to f of x. So she has obtained the answer of the computation that she wanted to perform. So f of x, but the server she can keep her data x private, because the server does not learn x. The server has only seen the encryptions of x. So the server has performed some computation on x, but without seeing x. He has performed this computation only on ciphertext, thanks to this homomorphic property. And it would also be possible to keep the function f, so not private. So not only x can be kept private, but also the computation itself, the function f, can also be kept private from the server. So there was a first generation of fully homomorphic encryption. So there is the breakthrough scheme of Gen 3, which solved basically this open problem, which did exhibit the first plausible construction of FHE. But the construction was relatively complex. It's based on ideal lattices. So there was some optimizations which were described a bit later, but still the implementation is quite slow, because the public key size is a few gigabytes, and the time to perform a recryption. So I will explain that, but basically a single evaluation of a XOR or of an AND is very long. It takes 30 minutes. For 30 minutes to evaluate any given gate. And so there was an alternative scheme which was much simpler. So because computation is performed over the integers. So this is the Dghv scheme. And for this scheme, one obtains approximately the same level of performances. So it's the public key size is relatively large, and the time to perform this homomorphic operation is still very long. Here, 15 minutes. So, but the advantage of this scheme is that it is quite simple because it works simply over the integers, so very simple. And so for now to explain the construction and the construction of fully homomorphic encryption, I'm going to focus on this scheme. So how does it work? So we start with a ciphertext M, which is a single bit. So we encrypt a single bit. And the encryption of M is simply a ciphertext C, which is Q times P, where P is the private key, so which is constant, and Q and R are random. So we are computing C equals Q times P plus 2R plus M. So, and R is a random which is smaller than P. And then we add the message M. So we have Q which is quite big, and R is small, relatively small, and smaller than the prime P. And to decrypt, it's quite simple. We simply reduce modulo P, the ciphertext. So this removes the term Q times P, and we assume that R is smaller than P. So we recover 2R plus M exactly over the integers. And so this means that when we reduce modulo 2, we recover the message M. So we see that these two random values, Q and R, which are fresh for every new ciphertext, we must generate a new random value for every ciphertext. These two random values are necessary because, of course, if we don't have Q, then we don't have an encryption scheme, because we can, if we don't have the term Q times P, we can simply read the message M as the least significant bit. But we must also add this 2R, because otherwise, if we simply have Q times P plus M, we can simply recover the private key by taking GCDs. Because in that case, if we assume that M is equal to 0, and if we have two exact multiples of P, then of course, by taking the GCD, we recover the private key. So this random R is really necessary to prevent the GCD attack. So as we will see, we must use very large parameters. The size of the ciphertext must be roughly 20 million bits for a reasonable level of security. So this is a huge expansion, because every bit is encrypted to 20 million bits. And the prime P must have roughly 2,700 bits, and the randomness R as a size which is roughly 71 bits. So we have a huge ciphertext size. But still, so this scheme is very simple, but we can see that it exhibits very basic homomorphic properties, because if we have two ciphertexts, C1 and C2, so C1 equals Q1P plus 2R1 plus M1, and C2 equals Q2P plus 2R2 plus M2, if we compute the sum, simply the sum over the integers of C1 and C2, we obtain some multiple of P, so Q1 plus Q2 times P, plus 2R prime, so R prime is R1 plus R2, plus M1 plus M2. And this is actually an encryption of M1 plus M2, because of M1 plus M2 modulo 2, because actually we only recover the sum M1 plus M2 modulo 2, because the carry is masked by the randomness in R prime. So this means that given an encryption of M1 and encryption of M2, we can obtain an encryption of the XOR of M1 and M2. And this is the same for multiplication. If we compute the product of two ciphertexts C1 and C2, we obtain C1 times C2, which is a multiple of P, plus 2 times R second plus M1 times M2, where we can check that R second is 2 times R1 R2 plus R1 M2 plus 2 M1. So we see that here C1 times C2 is an encryption of the product of the AND of the bits M1 and M2. So we see that the scheme is homomorphic for the two operations, addition and multiplication. But actually, the problem is not solved. We don't really have a fully homomorphic encryption scheme, because the noise, so what we call the noise in R, is growing. And in particular, for the multiplication, the size of the noise, the new noise R second, is twice larger than the initial noise. So for example, if the initial noise R1 and R2 have 70 bits, the new noise is roughly 140 bits. So its size has doubled. And for the addition, the noise is growing much more slowly because we are adding at most 1 bit of noise every time we perform an addition. It's for the multiplication that the noise is growing very, very quickly. So that's why actually, since the noise, when the noise is growing, we can only perform a limited number of multiplications, because when the noise becomes too large, when the noise becomes larger than p, then we cannot decrypt anymore. So and the decryption becomes incorrect. So we can only perform a limited number of multiplications. So that's why we don't really have a fully homomorphic encryption scheme in which the number of multiplications will be unlimited. So, but we can still write this some similar commutative diagram for the Dghv scheme, and in that case, the homomorphism is simply the reduction modulo p of the ciphertext, which eliminates the q times p part, and then the reduction modulo 2, so which gives us the message. But as I said, this only works if the noise R is smaller than p. Otherwise, decryption becomes incorrect. So we have this commutative diagram in which when we have two ciphertexts, we can perform this public operation, addition and multiplication, which I denote in green, to obtain a new ciphertext. And when we decrypt this ciphertext, we obtain a single bit in Z2. But if we follow the other path, if we decrypt those two ciphertexts and we XOR the two corresponding bits, the two plain text, or if we compute the AND, we obtain, of course, the same result. So we have a scheme which is, that's why we say that the scheme is somewhat homomorphic, because it can perform a limited number of homomorphic operations. So in particular, the number of multiplications is limited. So why is it limited? It's because the noise is growing exponentially with each layer of multiplication. So initially, we have a noise which is only raw bits with fresh ciphertext. But if we multiply two such ciphertexts, the size of the noise becomes 2 raw. And if we multiply again two such ciphertexts, the noise becomes 4 raw. And at some point, when the noise becomes larger than the prime p, then the decryption can become incorrect. So we cannot proceed with new multiplications. So this is because the size of the noise is growing exponentially with the number of layers, with each layer. At the first layer, the noise, at the initial layer, the noise is raw, then it's 2 raw, then 4 raw, then 8 raw. So it's growing exponentially with the number of multiplicative layers. So for now, we have described only a symmetric key encryption scheme, where to produce a ciphertext C, we must know the private key P. But it's easy actually to transform it into a public key encryption scheme, and for this we are going to use the additive homomorphic property. So for this, we simply publish a set of encryptions of zeros. So we publish xi's, which are qi's times p, plus 2r'i's, so encryptions of zeros. And then to encrypt a message M, we simply compute a random subset sum of the xi's. And so this subset sum remains an encryption of 0. And 2r is also an encryption of 0. So eventually we obtain that C is also an encryption of the message M. So a small problem that we have is that for the Dghv scheme, when we multiply two ciphertexts over the integers, so when we compute the product of C1 and C2, then the size of the ciphertext has doubled. And so, but we would like to bound to actually the ciphertext size. But for this, there is a simple trick. We simply publish an encryption of 0 without noise. So we publish an exact multiple of p. So we publish x0 equals q0 times p. Of course, we can only publish a single exact multiple of p, because if we have two such multiples of p, then we can compute the GCD and recover the private key. And then, thanks to this x0, we can reduce the product modulo x0. So we compute C1 times C2 modulo x0, and we obtain Q second times P because we have subtracted a multiple of P plus the same 2R prime plus M1 times M2. So this remains, this ciphertext C3 remains an encryption of M1 times M2 simply because we have subtracted a multiple of P. And now the advantage is that the ciphertext size remains constant. It is always smaller than, the ciphertext is always smaller than x0. But still we have the problem of the public key size, because we must have every ciphertext in the public key, every encryption of 0 has 20 million bits, as we have seen. This is the size of a ciphertext to get security, but in the public key we must have, also for security reasons, we must have something like 10 to 4 10,000 ciphertext, 10,000 XIs. So this means that the public key size, when we multiply the two, is roughly 25 gigabytes, which is a lot. But fortunately, there is a simple trick to compress the ciphertexts when we generate them in the public key. So you remember that the ciphertext is Q times P plus 2R plus M, where the ciphertext has size 20 million bits, but P is much smaller. It's only 2,700 bits. And so for this, the trick is to compute a big random number of the same size of the ciphertext C using a pseudo-random generator, using a public seed. So we expand this seed into a large random number, which has gamma bits, so the same size as a regular ciphertext. But of course, so this big integer key is not a ciphertext, because it has no structure. But it's easy to make a small correction so that it becomes a regular Dghv ciphertext. For this, we simply compute this correction delta, in which we subtract to key 2R plus M modulo P. And when we compute the difference, the new ciphertext C, which is the difference, then the difference modulo P becomes equal to 2R plus M. So this means that it is a Dghv ciphertext. And now the advantage is that we only have to store this small seed, and also the small correction delta. So this means that since this correction delta is modulo P, we only have to store a correction of 2,700 bits instead of 20 million bits. So eventually, when we do this for the full public key, instead of storing a public key of 25 gigabytes, we only have to store a public key of roughly 3.4 megabytes, so which is much more convenient. So we can ask, what is the security of this scheme, of this Dghv scheme? So what we want, at least, is to achieve semantic security, so which means that knowing the public key, we cannot distinguish between the encryption of 0 and the encryption of 1. So these two distributions should be hard to distinguish if we have a limited amount of computing power. And so one can prove that the Dghv scheme is semantically secure under the Approximate Gcd Assumption. So what is this Approximate Gcd Assumption? So the Approximate Gcd problem is that we are given a set of Xi's, which are near multiple of P, so Qi times P plus Ri, plus some noise Ri, and the goal is to recover the prime P. And so one can prove that the Dghv is secure, assuming that this problem is hard. And one can also prove that this remains the case even when we have compressed the public key, and for this we have to work in the random oracle model. So now we can consider this approximate GCD assumption. So what is the most efficient algorithm to break this approximate GCD assumption? So now actually we must consider a slight variant of this problem, which we call the partial approximate common divisor assumption, because we are given this additional value x0, which is an exact multiple of p. So we are given x0, which is p times q0. And we are given polynomially xi's, which are pqi's plus ri, and the goal is to find p. So the simplest attack is a brute force attack on the noise. So we are given x0, and we take x1, and we simply try to guess the value of R1, so which has row bits. So we guess R1 and we compute the GCD of x0 and x1 minus R1 for all possible guesses, and for the correct guess we recover the prime p, or actually a small possibly a small multiple of p, but it's easy to remove the small prime factor. So this requires 2-to-row GCD computation. So this takes exponential time, and so the countermeasure against this attack is simply to take a large enough row. So for the approximate GCD problem, there is actually an improved algorithm with a better complexity. So we are given x0, which is an exact multiple of p, and many xi's which are equal to p times qi's plus ri, and the goal is to find p's. But as previously, we are going to use only a single one, only x1. So we rewrite the equation with p. We write it as p equals GCD of x0 of the product of x1 minus I for I between 0 and 2 to rho minus 1. So, and for the right value of I, when I is equal to R1, then we have that x1 minus R1 is equal to 0 modulo p. So it's a multiple of p. So the GCD will give us so either exactly p or a small multiple of p. So for now, we have gained nothing, because to compute this product, it takes 2 to rho time. But we can rewrite this product. So we split the variable I in two parts in the middle. So where the middle is given by this variable m, which is 2 to rho over 2. So this constant m. And so we write I equals b plus ma, where b is the lower order bits between 0 and m minus 1, and a is the higher order bits between 0 and m minus 1. So we have these two parts, and we have this double product. So and the trick is to rewrite this as the product of the evaluation of a polynomial f. So f will be a polynomial of degree m in the variable in the b variable. So we write f of y equals the product for b equals 0 to m minus 1 of x1 minus b minus m times y. And so we see that here what we obtain is the product for a between 0 and a minus 1 of f of a modulo x0. So we see that now we must evaluate this polynomial f, which is of degree m, so 2 to rho over 2, and we must evaluate this polynomial in m points, and which corresponds to the values of a. And actually there exists an efficient algorithm that can evaluate such polynomial f of degree m at m points, and in time 2 to rho over 2, in time big O of m up to logarithmic factor, whereas the naive algorithm will be m squared. So that's why eventually we obtain an algorithm with complexity 2 to rho over 2 instead of 2 to rho. So this is for the brute force attack against the noise, which is easy to prevent. We simply take a large enough noise. But there is also a lattice attack. So we assume that we have t integers xi's equal pi qi's plus ri's, and also this exact multiple of p. And so the attack consists in looking for a vector u orthogonal to the xi's, orthogonal modulo x0. So we are looking for a vector u with ui's, the sum of the ui's xi's is equal to 0 modulo x0. And so when we reduce modulo p, we obtain that the sum is equal to 0 modulo p. And now the observation is that if the ui's are small, if the coefficients ui's are small, since the ri's are also small, then this sum will be smaller than p. And so this means that the equality will be over the integers. So the sum will be equal to 0 exactly, not only modulo p. So this means that we have obtained a vector u orthogonal to the RIs. And so such vector u, and actually many vector u's, can be obtained using lattice reduction, using the LLL algorithm. And then so we are going to collect many such orthogonal vectors, and once we have enough such vectors, we can actually recover R, the unknown R, and eventually the secret key P. So the complexity of this attack depends on the size of the XIs. And so to be secure, to have an attack of exponential complexity, we must have we must take a large enough gamma, a large enough ciphertext size. So that's why actually these XIs must be huge. They must have at least 20 million bits. So let me recap the Dghv scheme. So we have the key generation, in which we generate the XIs. So now we are going to change the definition a little bit. So we are going to write XIs equals P, QIs plus RI, and then there will be a factor 2 in the encryption, in the public key encryption, to make sure that these are encryptions of zeros. And so we have x0, which is p times q0, where p is the private key, secret prime. So to encrypt a message M, we generate random epsilon i's and random bits epsilon i's, and we generate a random R, and we would put the ciphertext, which is M plus 2R plus 2 times the sum of the epsilon I xi's, modulo x0. And to decrypt, we see that when we reduce modulo p, we obtain that M is M, the ciphertext C modulo p is M plus 2R plus 2 times the sum of the epsilon I ri. So which means that when we reduce modulo 2, we recover the message M. So we have seen that in that case, the noise in a fresh ciphertext is equal to C is M plus 2 times R prime, where so the noise R prime is R plus the sum of the noise in the public key XIs. And so this noise must remain smaller than P for correct decryption. So we have seen that we can add two ciphertexts. So this addition we do this modulo x0, and then in that case we obtain an encryption of M1 plus M2 of the XOR of M1 and M2, M1 plus M2 modulo 2. And so this works if the noise, the new noise R prime 1 plus R prime 2 is less than P. And so for multiplication it's the same. We compute the product modulo x0, and we obtain that the product C1 times C2 is an encryption of the product M1 times M2. So the scheme is homomorphic also for the multiplication. And so this works if the noise, the new noise, R prime 1 times R prime 2 approximately remains less than P. So but now we see that the noise has increased a lot, so its size has doubled. So this means that we have not quite obtained a fully homomorphic encryption scheme. We have obtained a partially homomorphic scheme because the noise grows with every multiplication, every addition and multiplication, but that's especially the case for multiplications. And so this limits the amount of multiplications that we can perform. So this means that this limits the degree of the polynomial that we can apply on ciphertext. So if we can do a maximum of d multiplications, this means that roughly we can evaluate a polynomial of degree at most d on the ciphertext. So now I'm going to explain what is the technique of Gentry with the bootstrapping to get a fully homomorphic encryption scheme. So we want to be able to perform an unlimited number of multiplications. So for this, we must find a way to decrease the amount of noise. So intuitively, this seems impossible because every time we perform an addition or multiplication, the noise can only increase. But we see that there is actually a technique which is quite powerful to actually reduce the amount of noise in a ciphertext. So let me recall the commutative diagram. So this time I'm going to consider a set of T ciphertexts and of T bits. And so we have seen that we can only compute a limited number of multiplications on ciphertext. So this means that the degree of the polynomial f that we can evaluate homomorphically is limited. It must be smaller than some value d. So this means that if we have t bits as input, we can compute any multivariate polynomial in the bits of this input, but the degree of this polynomial must be smaller than d. So we can combine at most d bits at a time, and not more. And so we have this commutative diagram in which if we start from t ciphertext, we can publicly evaluate homomorphically the function f on this ciphertext, and so we obtain a new ciphertext. And if we decrypt this ciphertext C on the right, then we on the bottom right we obtain exactly the same answer as if we follow the overpath. If we first decrypt each ciphertext separately, and then we compute the function f on the bits of the plain text. So now the breakthrough idea of Gentry is to actually use to refresh the ciphertext using the decryption circuit homomorphically. So we are going to, as a function f, we are going to use the decryption circuit of the scheme, the decryption circuit itself. And so in that case, so if we look at this decryption circuit, we know that this decryption circuit would take as input the bits of the ciphertext and also the bits of the secret key. It would combine these bits in some way, and eventually on the left we obtain the final plaintext bit, which is a decryption of the ciphertext. But now the technique is to do exactly the same computation but homomorphically. So we are going to evaluate the decryption polynomial, the decryption circuit, homomorphically. So for this, we are going to work on ciphertext. So we are going to encrypt every bit of the ciphertext, to expand and to encrypt every bit of the ciphertext separately. And we also encrypt every bit of the secret key. So actually, for the ciphertext bits, we don't really have to expand the ciphertext, because actually 0 is an encryption of 0 and 1 is an encryption of 1 in the Dghv scheme. So we can keep actually the same bits. We don't have to increase. Otherwise, the size will be squared. We will have gamma square bits, which will be huge. But here, actually, we can keep the same bits. But of course, for the encryption of the secret key bits, we must really provide these encryptions. So now, what happens when we evaluate this decryption circuit? We obtain exactly the same answer as on the left, but we obtain an encryption of the plaintext bit. So this means that we obtain a new ciphertext for the same plaintext bit. So we start from a ciphertext. We consider every bit of the ciphertext separately. We apply homomorphically the decryption circuit, and we obtain a new ciphertext for the same bit. But so we could think that we have obtained nothing, but actually this new ciphertext has a noise which depends only on the depth or on the number of multiplications or on the degree of the decryption circuit. If this decryption circuit has a small degree, then the new noise in the new ciphertext can be smaller than the initial noise, because this decryption circuit it works for any ciphertext as input. So even if the noise in the input ciphertext is very large, the decryption will still be correct. And so even if as input we have a large noise, the new noise in the new ciphertext depends only on the depth of the decryption circuit. So it can be smaller. So in this case we say that we have refreshed the ciphertext. We obtain a new ciphertext for which the amount of noise has decreased. So this is the bootstrapping technique. So I'm going to describe this bootstrapping technique a bit differently, because it is very, very, very powerful. So as I said, this consists the bootstrapping technique evaluates the decryption function f homomorphically. So we consider this decryption function f, and so if we look at this commutative diagram, at the bottom in the plain text world, if we write the bits of the ciphertext, so we assume that the ciphertext has t bits, and so we write all the bits of the ciphertext. Since f is the decryption circuit, the decryption polynomial, when we evaluate this polynomial f at the bottom, we obtain the message m, the bit m on the bottom right. But now, if we perform the same with ciphertext, we start from encryption of every ciphertext bit, so the encryption of the CIs on the upper left. Then, when we apply this circuit homomorphically, when we evaluate the function f homomorphically, we obtain a new ciphertext C star, and which has possibly less noise, because the noise in the new ciphertext only depends on the depth of the function f, on the degree of the function f. So, but actually we must do something a bit differently. We must actually use the decryption function that takes as input both the secret key and also the ciphertext to be decrypted. So, and for this, we are going to use public encryptions of every single bit of the secret key. So this is a bit the same as previously. So this time we assume that we have a function f, a circuit that takes as input the bits of the secret key. So I assume that we have t bits of the secret key and the t bits of the ciphertext. So here, for simplicity, I assume that they have the same size, but of course they don't necessarily have the same size. So in that case, in the plain text world, if we take as input the bits of the secret key and the bits of the ciphertext, eventually when we decrypt, we obtain on the bottom right the message m. But if we do the same in the ciphertext world, at the top, if we have in the encryption of the secret key bits, the encryption of the SKIs, and the encryption of the ciphertext bits, the encryption of these CIs, when we publicly evaluate the decryption function f, we obtain eventually a new ciphertext C star as previously, but with possibly less noise. So this is a ciphertext refresh. And so, but for this, actually, it must be the case that the decryption function, this f, must have a small degree in the inputs. And actually, this is not the case if we consider the regular decryption function of Dghv, because in that case, the decryption function is C modulo p and modulo 2. But if we look at it, the depth is not small in terms. If we write if you write this decryption function as a function of the bits of p and the bits of c, the depth is huge. So the technique to reduce the depth is to slightly modify the scheme and to modify the decryption procedure. So our goal is to express the decryption function as a low degree polynomial in the bits of the ciphertext and in the bits of the secret key. So and I will explain how this is done with Dghv scheme. So now assume that we have obtained a refresh ciphertext. So if the degree of the decryption polynomial is small enough, then the noise in the new ciphertext can be smaller than in the original ciphertext. So we start with a ciphertext C with a lot of noise, and eventually we obtain C star, which has less noise. And so now we can always perform this ciphertext refresh to decrease the amount of noise. So this gives us a fully homomorphic encryption scheme, because the number of homomorphic operations becomes unlimited. So if we want to multiply two ciphertexts, so if they have too much noise initially, we cannot do this multiplication, because otherwise the noise will become greater than p, and then decryption becomes incorrect. But still, what we can do is we can refresh both ciphertexts, and now the noise is small enough, so we can perform one more multiplication. So we repeat this procedure. We always refresh a ciphertext that is too noisy. So eventually, the number of ciphertext, or the number of homomorphic operations becomes unlimited, and so we obtain a fully homomorphic encryption scheme. So as I said previously, one difficulty is that for the basic decryption procedure of the Dghv scheme, when we reduce the ciphertext modulo p and then modulo 2, this cannot be expressed as a Boolean circuit of low depth, because if we look at it, we see immediately that the depth is huge. So instead, we have to modify the decryption procedure. So for this, we are going to first consider some alternative decryption formula for ciphertext. So ciphertext Q times P plus 2R plus M. So we see that Q is almost the quotient. Actually, it's not exactly the quotient because R can be negative, but Q is the rounding to the nearest integer of C over P. And then when we have Q, we see that C is equal to Q plus M modulo 2. So, which means that now we can use a slightly different equation for the decryption. The message M is the ciphertext C modulo 2, so the least significant bit, XORed with the rounding of to the nearest integer of C times 1 over P, and then reduced modulo 2. So we have this alternative equation. And thanks to this alternative equation, there is this idea of gantry and in the Dghv scheme to secret share the secret 1 over P as a sparse subset sum. So we write 1 over P as a sum for theta elements of si's times yi's plus some epsilon. So the yi's are public numbers with a fractional part, and the si's are bits and secret bits. So the yi's are public and the si's are secret bits. And moreover, the vector of the si's is sparse. That is, most of the si's are 0 and only a small number of si's are 1. And so so as I said, we have this alternative equation. So we secret share 1 over P as a sparse subset sum. And so with precision 2 to minus K, where K corresponds to the size of a ciphertext, and we have a sparse secret si's. And so when we rewrite this equation, we obtain that M is the XOR, so same part with the C modulo 2, and we have the sum of the si's, yi's times C, which is rounded to the integer, to the nearest integer. And now the observation is that since the si's are sparse, we can actually use a very small amount of precision in the yi's times C. So actually, so we can rewrite this equation as zi equals yi times c, which we can compute given a ciphertext because the yi's are public. And so since one can show that since the si's is a sparse vector where only a small number are non-zero, for example, we take only 15 values which are non-zero, we can use a limited number of precision. So we need only 4 bits of precision when theta is equal to 15. So the formula is log 2 of theta plus 1 bits. So this means that since we use a very small number of bits of precision for the ZIs, the decryption function can be expressed as a polynomial of low degree in the bits SIs. Actually, the degree is actually only 30. So so this decryption function now as a small degree as required for the bootstrapping. So and actually to reduce the degree, we can have there is another technique by Gentry and Levy. So we know that there are only small theta bits, only 15 bits of the secret SI which are non-zero. So we are going to split the secret key bits into theta boxes of size big theta over small theta each. And so this means that inside every box, there is only one bit which is equal to 1. So this gives, so we split the sum into the boxes. And so this gives that a sum over all the small theta boxes. And then we do the sum over in a given box. So which means that now we can rewrite this as qk. If we write qk as a sum in a box, we obtain that we are adding big B numbers, the size of the box, but by construction there is only one which is non-zero. So the rest is equal to all the other terms is 0. So this means that actually, since there is only a single term which is non-zero, the arithmetic sum is the same as a XOR. We can simply XOR all the terms, and we obtain the same result because actually there is only one term that is non-zero. The others are 0. So this means that to compute the Dghv bit of qk, we simply to have to XOR all the Dghv bits of the numbers ski times zki. So this is illustrated in the decryption circuit in this figure. So we have if we have the encryption, so we have the bits of the secret key. So in a given box there is only one bit which is equal to 1, so it gets multiplied to the zi's. And so after it gets multiplied, there is only one value which is non-zero. So instead of computing the arithmetic sum, we can simply XOR all those values, and which is interesting because the XOR corresponds homomorphically to a simple addition of ciphertext, which is very fast. But eventually, we must compute the arithmetic sum of the QIs. And so we have, so the Hamming weight of the secret key is only 15, so for example, and so we must compute the sum of 15 such QIs. And eventually one can show that the plain text bit is the XOR of the most significant bit and the next bit. So to perform this homomorphic, this bootstrapping, we must actually build and consider this decryption circuit that we are going to evaluate homomorphically. And so, in particular, we must consider the final grade school, the final addition. And so we are going simply to perform a grade school addition of the QKs. So this means that we are going to propagate a carry, so that eventually we compute this addition, but with a very small number of bits. We only have 5 bits, a total of 5 bits. And eventually, as I said, the final decryption, the final message is the XOR of the most significant bit and the next bit. So we must write this decryption circuit, and then once we can express this decryption circuit as a polynomial of small degree d in the bits of the secret key, in the bits of the VSIs. And so we have seen that the degree is actually 30. So it's not too large. So the message M can be expressed as a polynomial or small degree d in the security bits SSIs. And now to refresh a ciphertext, to do the bootstrapping, we assume that we have a public encryption of the bits of the secret key, so the sigma I are encryptions of the SIs, and so we perform exactly the same computation but homomorphically. So we use the encryptions of the secret key bits, and eventually we obtain an encryption of the message M when we perform this homomorphic evaluation. And this is a new ciphertext, but with possibly less noise. Actually, the new noise has size roughly d times row bits, because we have performed the degree is d, and so we perform at most d multiplications. And so the new noise is roughly d times rho. And so this can be smaller than the noise from which we have started in the original ciphertext. So that's why eventually we really have a refresh of the ciphertext and eventually a fully homomorphic encryption scheme. So as I said in the beginning, we have these 4 generations of fully homomorphic encryption that we can distinguish. So in the first generation, we had this invention of the bootstrapping, which is so powerful, but actually relatively slow because it takes a few minutes to perform a refresh of a ciphertext. So this means that to process a AND gate, it takes a single AND gate homomorphically. It takes a few minutes. So it's very slow. And so I have described how it works for the Dghv scheme, the FHE over the integers. So now I'm going to describe relatively briefly the other generations of FHE that have appeared in the last 10 years. So in the second generation, we have schemes that are based on the learning with error problem, or the ring learning with error problem. So which is more efficient than working over the integers. So so I will describe the techniques that are necessary. So the relinearization technique, and also the modulus switching technique that enables to have a construction where the size of the parameters is linear in the depth of the circuit to be evaluated. So I will explain what it means. And then we have this third generation in which the ciphertexts are matrices. And the advantage of this new generation is that the noise can grow very slowly. So we can perform many homomorphic operations without the noise to grow too much. And we have also improved bootstrapping procedures. And we have this also a fourth generation in which we perform computation on floating points, which can be interesting for some applications. For example, to evaluate a neural network, the weights are floating points, and the inputs also are floating points. And so we can do this evaluation homomorphically in an efficient way. So let me now describe the second generation of fully homomorphic encryption scheme. So they are based on polynomials and polynomial evaluation. So the homomorphism consists in evaluating such polynomial. So we consider a linear polynomial with coefficients modulo q with n variables. And so it's a linear polynomial. So we have n plus 1 coefficients with the constant term. And so the homomorphism, the decryption function, consists in evaluating this polynomial at some secret point S with n components. So this is an homomorphism. So we still have this commutative diagram. If we take two polynomials, we can add those two polynomials, or we can compute the product of these two polynomials. And when we decrypt on the right, we obtain the evaluation of the result is the same as if we first evaluate the polynomial at S and compute the sum or the product of these evaluations of the plain text. But of course, like this, it does not work. It's not secure because everything is linear. If we have a linear, if we have because the unknown has only n components. So if we have n ciphertexts that we know, and if we know their evaluations by solving a linear system, we can easily recover the secret key. So as previously, we must have we must add some noise. So because otherwise it's broken by linear algebra. So we assume that the evaluation of a polynomial f of a ciphertext at S is equal to 2e plus m modulo q for some small noise e modulo q. So e will be much smaller than q. In that case, linear algebra does not work anymore. And so the security is based on the learning with error assumption. So we have a collection of linear polynomials fi of x, such that when they get evaluated at the secret point S, this evaluation is much smaller than q, and we assume that it is hard to distinguish from completely random polynomials. So how does it work? So eventually we can construct a public key encryption scheme based on this, and this is the scheme by Dghv. So we have the secret key, which is this secret point with this secret vector with n components, and the public key is a collection of polynomials fi of x, such that when evaluated at s, we obtain 2 times ei for some small noise ei. And then to encrypt a bit m, we compute, as previously, a random subset sum of these ciphertexts in the public key, which are encryptions of 0. So we compute the sum of the BIs times fi of x for random BIs plus the message m. And then when to decrypt, we evaluate the ciphertext C, the ciphertext polynomial, at the vector S, and so we obtain m plus 2 times the sum of the BIs times EIs. And so when we reduce modulo 2, we recover the message m. So the scheme is quite simple. And so the problem that we have is that when we perform a multiplication of ciphertext, the size of the ciphertext increases. So if we have two polynomials, C1 and C2, if we add those two polynomials, so we obtain a ciphertext, a new polynomial with the same degree. So it's not a problem, and the scheme is homomorphic for the addition. But if we perform the product, so assume that we have two ciphertexts C1 of x and C2 of x. If we compute the product, C of x equals C1 of x times C2 of x, when we evaluate this product polynomial at S, we obtain M1 plus 2 times E1 times M2 plus 2 times E2. So this is M1 times M2 plus 2 times some new noise E, modulo Q, so which is good. So this means that we have obtained an encryption of M1 times M2. So the scheme is homomorphic for the multiplication. But the problem is that now the polynomial C is a quadratic polynomial. So it has n plus 1 square coefficients. So instead of n plus 1 in the original ciphertext, C1 of x and C2 of x. And so to reduce the amount of the number of coefficients, to have a constant size for the ciphertext, there is this relinearization technique. So the technique consists in publishing polynomials where we exhibit a single quadratic term, so xj times xk, multiplied by 2 to t, because we are going to perform a binary decomposition, plus some linear term, a classical linear polynomial. And so we generate these polynomials in such a way that when they evaluate at S, we obtain, again, a small noise, or 2 times some small noise. And so now we can actually, thanks to these polynomials PGKT, we can remove the quadratic terms. So because simply by subtraction. And actually, when we have a quadratic term AGK times XG times XK in the product ciphertext, we can remove this term by subtracting the right polynomials PGKT. And so for this we also use a binary decomposition of AGK. So we must use a binary decomposition to keep a small noise, or otherwise the noise would grow too much. And so eventually only the linear terms remain, and so we obtain a new ciphertext for the same that encrypts the same message, but the ciphertext size remains constant. And so we have also a new technique, which is the modulus switching, which appeared in the Dghv scheme 10 years ago. So for simplicity, I'm going to rewrite the ciphertext polynomial as a vector of coefficients. So the ciphertext polynomial is simply the product of the scalar product of the coefficient vector C with 1 for the constant term and the vector x for the other variables, modulo q. So assume that we want to switch from an encryption modulo q to some new prime p, and I will explain why this is useful. And for this, actually, this is quite simple. With this scheme, we simply have to perform some scaling of all the coefficients independently. So we define a new vector C prime, which is the vector closest to P over Q times C. So we scale all the coefficients separately, and we do this such that the value modulo 2 of the coefficients remains the same. And in that case, one can easily show that the decryption remains the same. So the new ciphertext decrypts to the same plain text. But now the advantage is that we have decreased the amount of noise, because the noise is also scaled roughly by P over Q. It is reduced by a factor Q over P. And as an application, we can reduce the growth of the noise. And we can do this without the bootstrapping procedure, which is quite costly. So I assume that we have that P over Q is roughly 2 to minus rho. In that case, we start if we start from a ciphertext with rho bits of noise, if we perform a multiplication of ciphertext, the size of the noise has doubled, so we get 2 rho. But now we can perform this modulus switching, and we scale the ciphertext to modulo P, and in that case, if the ratio is 2 to rho between P and Q, the noise gets back to rho only. So this means that we have reduced the amount of noise, but without using the bootstrapping. But the price to pay, of course, is we have also reduced the size of the modulus. So we started from a modulus Q, and now we have a modulus P. But actually, this procedure is very useful and very important, because this enables to have a linear growth of the noise instead of exponential. So in the previous model, when we worked with the Dghv scheme, the noise would grow exponentially with the depth, with each layer of multiplication. So we start with noise equals 2 rho, then it becomes 2 rho, and the next layer of multiplication is 4 rho and 8 rho. So it grows exponentially, and then we are stuck because the noise is too large. And then the only technique to reduce the amount of noise in that case is to use bootstrapping, but this is quite costly. But here we have a new model in which we can perform the modulus switching after each multiplication layer. So we start with a ciphertext with noise rho, and we multiply two such ciphertext, we get 2 rho, and then we can perform the modulus switching. So we switch to a new modulus P2, and we have noise rho again. So if we perform a new multiplication, we have 2 rho as a noise, and then we can again perform a modulus switching, and to get rho again, and then 2 rho, and so on. And so we see that, and for this we need to use a ladder of moduli pi, such that the ratio between two successive pi's is roughly 2 to minus rho. And this enables to obtain what we call a leveled fully homomorphic encryption scheme, because what we see in this picture is that the size of the modulus P1, of the initial modulus P1, is linear in the circuit depth, because for every new layer we reduce the size of the modulus by rho. So this means that if we have a depth which is d, the size of P1 must be linear proportional to d. And so this means that the number of multiplications that we can perform, or the number of layers that we can evaluate, must be known in advance. And then we compute the parameters as a function of the depth. So that's why we say that we have a leveled fully homomorphic encryption scheme. We must know in advance the number of levels. But we really have a fully homomorphic encryption scheme, because we can evaluate a circuit with any depth, because the size of P1 is only linear in the depth. So this means that we have obtained a fully homomorphic encryption scheme, but without using the bootstrapping, simply using the modulus switching. And alternatively, instead of working with the learning with error problem, so recall in Dghv schemes we are working modulo Q, we are working with polynomials with coefficients modulo Q, and we can actually replace ZQ by a polynomial ring. So for example, the polynomials modulo q, modulo xk plus 1, where k is the power of 2. So we have, because actually the scheme by Dghv works in any ring, not only modulo q. And so in that case, in this ring, we perform the addition and the multiplication of polynomials modulo xk plus 1, modulo the prime q. And actually, in that case, in the previous scheme, we can actually take n equals 1. So we have the secret key as a single component, which is an element of the ring. And an advantage of this scheme is that now we can encrypt a message m, which is not a single bit, but a polynomial modulo 2. So a polynomial modulo xk plus 1 and modulo 2. So this means that this polynomial has k coefficients, where k is the degree of the ring, instead of a single coefficient. So this means that we can encrypt many bits at the same time. So this improves the performance, and it saves on the bandwidth. So let me now describe the third generation of FFHE, which are based on ciphertext matrices. So so we are going to use square matrices instead of vectors. So ciphertext is a square matrix. And then the homomorphic operation that we consider is to compute the eigenvalue for a secret eigenvector v. So we assume that we have a secret eigenvector v, and all ciphertexts they have v as an eigenvector, and mu is the corresponding message is mu, which is the eigenvalue for this secret eigenvector. And now we see that if we add two such ciphertexts, then the eigenvalues they get added. And if we multiply two such ciphertexts, the eigenvalues get multiplied. So again, we have this commutative diagram. If we start from two matrices and we add or we multiply them, we obtain a new matrix. And if we decrypt this matrix, we obtain some eigenvalue, which is the same as if we have performed this, if we decrypt the two ciphertexts independently first, and then we add or we multiply the corresponding eigenvalues. So in that case, the eigenvalue can be any integer, not necessarily 0, 1. But we are going to see that it's more efficient if it's 0, 1. So as previously, this scheme is not secure, because we by linear algebra, by simply diagonalizing the matrix, we can recover all the eigenvectors and the eigenvalues. So there will be no security. So as previously, we are going to add some noise to prevent the linear algebra attacks. So it works like this. So now actually the vector v, the secret eigenvector v, is not really an eigenvector of the matrix C. It's only an approximate eigenvector. So this means this means that C times V is mu times V plus some error E. So we add this noise E. So the error E is a random is a small vector, small noise. And mu is the eigenvalue, the approximate eigenvalue is the message. And one can prove that the security is based on the learning with error problem for this scheme. And so the main advantage of this scheme is that the growth of the noise can be very slow. So for example, if we multiply two ciphertexts, so assume that we have two ciphertexts C1 and C2. C1 times V is mu1 times V plus E1, and C2 times V is mu2 times V plus E2. If we multiply two such ciphertexts, we obtain C1 times C2 times V. So we expand C2 times V, so it's C1 times mu2V plus E2. And when we expand C1 times V, we obtain mu2 times mu1 V plus a new error vector E3, where the error vector E3 is mu2 times E1 plus C1 times E2. So we see that the scheme is really homomorphic for the multiplication, because we have obtained an encryption of the product of the two eigenvalues of the two messages mu2 and mu1, but with a new noise. So now we can consider the growth of the noise. So what is the size of E3 compared to the size of the noise E1 and E2? And we are going to see that it can grow relatively slowly. So for this, we want to ensure that the message is only 0, 1. So we have seen that the message can be any integer, but it's more efficient for the growth of the noise if we only encrypt bits. And for this, we can simply rewrite our circuit with NAND gates. So a NAND gate, so any circuit can be computed with NAND gates. And in that case, the new eigenvalue is 1 minus mu1 times mu2. So it means that it must remain 0, 1. And then to prevent the growth of the noise, one can use a technique which is called ciphertext flattening. Actually, we can work with ciphertext with only binary values. And for this, so the components of the ciphertext are 0, 1 only. And for this, we use some binary decomposition of the ciphertext or some intermediate value, and we use also a special structure for the secret key. So the secret key will consist in powers of 2. So we start with, so for every bit of the original secret key, we compute S1 times 2, S1 times 4, and still 2 to L, where L is the bit size of the modulus Q. And by using this special structure, one can see that we can always work with ciphertext with binary coefficients. In that case, if we see with the formula with E3, if the infinite norm, if all the components of E1 are smaller than B, since mu2 is binary, this remains the same for the product. And for the product of C1 times E2, if the coefficients of C1 are 0, 1, and so it's a n by n matrix, the norm of C1 times E2, the infinite norm is smaller than n times B. So in total, it's n plus 1 times B. So the norm of the new vector, E3, is at most n plus 1 times B. And so this shows that the noise is growing relatively slowly, because for every multiplication, when the depth is equal to L, the noise will be roughly smaller than n plus 1 to the power of L times B. So this means that the size of the noise is growing linearly with the depth L. So this means that we can take a modulus Q, which has a size which is linear in the depth L. So this means that we can accommodate a depth which is polynomial. So instead of having a noise that grows exponentially with the depth, the noise grows only linearly. The size of the noise grows only linearly with L. So this means that, as previously, we obtain a leveled fully homomorphic encryption scheme. And so let me describe eventually the fourth generation of schemes, so which is homomorphic encryption for approximate numbers. So we like to perform floating point arithmetics instead of exact arithmetic. And we would like to do it in some efficient way. So of course we can always simulate floating point arithmetic with integers. But here we would like to do it more efficiently. So we start with the scheme by Dghv, and we use exactly the same homomorphism as previously, which is the evaluation of a polynomial, of a linear polynomial at some point S. So we have the same commutative diagram, but as previously we must add some noise. Otherwise, this will be broken by linear algebra. But this time we manage the noise a bit differently. We directly add the noise E, a small noise E, to the message M. So the evaluation of S will be M plus E. So this means that when we decrypt, we do not recover the original message M exactly. There is some noise, a small amount of noise that affects the lower order bits. So this means that we have only some approximate computation, as in floating point arithmetic. But we are going to see that this is much more efficient when we want to compute with floats, which is the case, for example, for neural networks, in which the weights are basically floats. So how does this work? Assume that we want to compute the product of two floating points which are encrypted. So we compute the product of the two ciphertexts. So we obtain a new ciphertext C, and when we evaluate this ciphertext C at S, we obtain, so we have M1 plus E1 times M2 plus E2. So we obtain the product M1 times M2 plus a new noise, E star, where E star is M1 E2 plus E1 M2 plus E1 E2. And so the noise has increased. But actually what we are, so to prevent the growth of the noise, we are going to do a rescaling of the ciphertext, which is a bit similar to the modulus switching. So we divide each coefficient of the ciphertext by p, and then we round, and we obtain a new ciphertext but modulo q over p. So we assume that q is a multiple of p, or a power of p. And we obtain that this is actually a valid encryption of the rounding of m over p. So when we perform this scaling of the ciphertext, the message itself gets rounded automatically, but with a noise that is reduced. Where the noise becomes E over P instead of E. So in this picture, if we start with two ciphertexts that encrypts M1 and M2, but with some noise E1 and E2, when we compute the product, we get M1 times M2, but when we do the scaling, we divide by P, and we obtain the same amount of noise as previously, so E prime. And so we have obtained the higher order bits of the product of M1 times M2 as in floating point arithmetic. So we can simulate floating point arithmetic with this scheme. So as a conclusion, so the main challenge, 13 years after the discovery of fully homomorphic encryption, the challenge is still to make fully homomorphic encryption practical. So for this, we probably need new primitives. We also need efficient libraries, so for example the HLib library, and we also need compilers to homomorphic evaluation, because we don't want to design or to work with the circuit to be evaluated. And so fully homomorphic encryption can have many applications, and so for example machine learning, if you want to evaluate a neural network without revealing the weights and without revealing the input data, and there are also many other applications.